Hello, and welcome to Climate Change 101 for Machine Learning Practitioners. My name is Priya Donti, and I'm a PhD student in Computer Science and Public Policy at Carnegie Mellon University.
Hi, my name is Lynn Kaack, and I'm a postdoctoral researcher at the ETH Zurich.
Hello, my name is Kris Sankaran, and I'm an assistant professor of statistics at University of Wisconsin-Madison.
Awesome. So today we're going to dive into a couple of things. So first of all, we'll try to provide an understanding for how climate change actually occurs and what its impacts are, how you actually go about addressing this, and who you would work with if you were to go about doing that. And then finally, we'll tie in the machine learning and talk about leverage points that machine learning has and maybe important considerations for actually doing machine learning in this climate change area. So to start with, what exactly is climate change and how is it caused? So to understand climate change, it's important to understand the distinction between climate and weather. To quote Edward Lorenz, climate is what you expect and weather is what you get. And so to put that in a different setting here, or in a different way here, weather refers to the short-term variations of the atmosphere on a span of minutes to days. So statements like, it's raining today, or it's going to be sunny tomorrow, are statements about the weather. Climate, on the other hand, looks at longer-term trends. So what is the average weather over a longer period of time, for example, 30 years? So a statement like, the global average temperature now is warmer than the global average temperature 30 years ago, is a statement about the climate. And then, as you can imagine, climate change is a change in the climate over time. So climate change occurs due to a phenomenon called radiative forcing. So radiative forcing is defined as the amount of energy going into the Earth minus the energy going out of the Earth. And to illustrate this concept, I'm going to show a diagram from the Intergovernmental Panel on Climate Change, IPCC. So this diagram, and there's a lot going on, so I'll walk you through it, I promise. This diagram shows the kind of energy fluxes in the Earth. So energy coming into the Earth, energy leaving the Earth, what happens kind of in between, expressed in units of watts per meter squared. So there are a couple of things I want to draw your attention to in this, again, very large, complicated diagram. The first is energy coming into the Earth. So this, as you can imagine, is coming from the sun. And then after the solar energy comes in, some of it is reflected. Some of it goes down to the Earth's surface and it's absorbed and then re-rated as thermal energy. And so the other thing to look at on this diagram is the amount of energy going out. So if you sum those numbers up really quickly, you'll notice that we have 340 watts per meter squared coming in and 339 watts per meter squared going out. So that means there's more energy coming in than there is coming out. And this is ultimately what's causing the Earth to warm. So we call this positive radiative forcing. And the reason it's occurring is because, as you can imagine, we have too many greenhouse gases in the Earth's atmosphere that are trapping too much heat. And greenhouse gases are basically defined to be gases that are transparent to solar energy. So they actually let the solar energy into the Earth, but they trap the heat energy that the Earth re-radiates that as. And then they kind of, they trap it back into the surface. And so on this diagram, to bring it back, the greenhouse gases are shown within the purple box. And you see that the greenhouse gases let a little bit of the thermal energy that is coming from the Earth back out, but a lot of it actually gets trapped back down. And this is what's sort of throwing off the balance of energy into the Earth versus energy out. There are a number of greenhouse gases that are present in the Earth's atmosphere. Water vapor is actually the most common. It makes up 90% of greenhouse gases by volume. But the one that we tend to think a lot about when we talk about climate change mitigation and adaptation, which are terms I will define in a moment, are carbon dioxide, nitrous oxide, methane. These are greenhouse gases that, first of all, have been increasing in their concentration because of human activity. So that's one reason we care about them. And another reason we care about them is that they actually tend to stay in the atmosphere for a long period of time and actually continue to warm the Earth well after they're actually put there. Whereas water vapor actually transition in and out of the atmosphere very quickly. When you see a cloud, it probably will rain at some point and that water vapor will come And so just to have kind of a standard unit by which we can express the potency of a particular greenhouse gas, we often use the terminology of CO2 equivalence. So basically, how efficient is a greenhouse gas at trapping heat? This is called its radiative efficiency. And then also, how long does that greenhouse gas stay in the atmosphere? That's called its residence time. And these two things together make up a global warming potential, which is then relative to carbon dioxide. So carbon dioxide has a CO2 equivalent global warming potential of 1, and other greenhouse gases have larger ones. So depending on the time frame you're looking at, for example, methane has 30 to 40 times the greenhouse gas, the global warming potential of carbon dioxide. So what else do we know here? So I'm going to throw up another large diagram from the IPCC, and I'm again going to do the thing where I break it down, so bear with me here. So again, large diagrams as promised, and a couple of things I want to take away from here. So on the x-axis of this diagram, we have year, in this case going from 1960 to in the future. And the y-axis has the amount of global warming that we see relative to the pre-industrial period, so 1850 to 1900 roughly. You'll notice in 1960, we had an above zero amount of warming, and that this has continued to go up. That in approximately 2020, where we are now, we have about a degree of warming already. And that this is caused by human activities. So basically the takeaway here, which you can read on the slide as well, the climate is warming due to human activities. And the amount by which we're actually able to reduce greenhouse gas emissions is going to affect the amount of warming that we see in the future. So on the right side here, the graph labeled B, on the x-axis, we again have year, and on the y-axis, we have the net global CO2 emissions that we see. And what you're seeing in the kind of bold turquoise line and the bold gray line are stylized pathways for greenhouse gas emission reductions that we might see. So there's a turquoise line that says we reach net zero greenhouse gas emissions by 2040, and the gray line shows what happens if we reach them by 2055. These turquoise and gray colors in the graph on the right side correspond to the warming pathways that you see on the left side. So for instance, where my mouse is, you can see kind of a turquoise upper bound and turquoise lower bound for the amount of warming that we would expect to see if we reached net zero emissions by 2040. And similarly, these gray upper and lower bounds are for net zero by 2055. And the purple ones are actually for the case in which we only look at carbon dioxide and which we don't mitigate other greenhouse gas emissions. And so the time scale at which we reduce greenhouse gas emissions will actually have a very large effect on the amount of warming that we see. And one last thing I'll point out on this left diagram is that horizontal line next to 1.5 degrees. So when you hear targets about, oh, we need to reach net zero greenhouse gases in 20 or 30 years in order to avert warming of 1.5 degrees Celsius, this refers to sort of our mean estimate for what's going to happen if we achieve certain net zero reductions. So, okay, so we know that there are emissions, that they are rising, and that this is causing warming. So where are these emissions actually coming from? So this diagram, again in the pattern of putting large complicated diagrams on these slides, shows where the emissions actually come from, broken down by sector. So in the first column is the actual sector. So for example, transportation, electricity, agriculture, land use. For those who have been kind of following the workshop this whole week, you'll notice that some of these sectors are actually the foci of different days that we've held this week. In the second column, this is actually broken down further by the actual end user activity, the way in which these emissions or the emissions from different activities that we actually do in these various sectors. So for example, road transportation, or using energy or electricity in residential buildings, or things like producing soils for agriculture. So that's what the second column shows. And then the third column shows the actual greenhouse gas that is emitted from various activities. So 75% of the emissions that we think about are carbon dioxide, but methane, CH4, and nitrous oxide, N2O, are actually really big contributors here as well. And so it's always fun to, have some of the numbers from this diagram off the top of your head. If you're somebody who likes to talk about climate change and likes to be able to do the thing where you're like, 30% of global greenhouse gas emissions come from electricity and heat, feel free to take a look at this diagram. The slides will be up. But the broad takeaway from this particular diagram is that there are many different places that emissions come from, which can be a little bit dizzying and disheartening to some people that there's so many, this problem is so distributed. But on the other hand, this can really be viewed as an opportunity. There are many different places where you can plug in and actually have an impact on trying to tackle the climate change problem. And so why do we actually care about climate change? And I'm going to argue that it's because it's an issue with real impact on human well-being. So this diagram, also from the IPCC, shows the impacts attributed to climate change around the globe. So the blue symbols that you see are impacts to physical systems, things like glaciers melting or flooding occurring or coastal erosion. The green symbols you see on the slide refer to impacts on biological systems, so things like wildfires occurring or your favorite fish becoming extinct. And then finally, the red symbols refer to impacts on human or managed systems, so things like food production taking a hit due to drought, or people's livelihoods or economic well-being being compromised. And again, lots of things to look at on this slide, but there's sort of 2 points I'd like to emphasize here. One of which is the impacts are going to be felt globally. There isn't really a place that is not going to be touched by climate change, and these impacts are often going to fall most heavily on the world's populations that are already the most disadvantaged. And as a result, working on climate change is really an issue of human well-being and one that we should take very seriously. All right, so doom and gloom on that last slide. Lots of impacts, emissions are rising. So what can we actually do? There are 2 main approaches that are often kind of talked about when it comes to tackling climate change. One of them is climate change mitigation, which basically means reducing the extent to which climate change will actually occur. And as sort of hinted at by the physical basis of climate change, the sort of physics behind climate change that I talked about earlier, the way you do this is by actually reducing the amount of greenhouse gas emissions going into the atmosphere. The second approach is climate change adaptation. So given that we do have some amount of greenhouse gas emissions already in the atmosphere, and given that this will inevitably lead to some amount of warming, and that we already are seeing warming right now, how do we build a society that is resilient and robust to these consequences that we know are going to occur? There are a lot of ways to think about how exactly do I trade off between mitigation and adaptation approaches. This term on the slide, integrated assessment models, is one that comes up quite a bit in, for example, IPCC reports, and so is one that I just wanted to put here so you're familiar with it. And integrated assessment models basically combine climate science, social factors, economic factors, etc., into a model in order to understand the costs of taking various mitigation actions, and then the benefits of doing that in terms of, for example, avoiding hits to the food system. So this is one way that we can look at, for instance, how much does it cost to implement a certain mitigation action and what are the effects of that? And then some models are starting to take into account what we can actually do in terms of adaptation. Now, integrated assessment models make a lot of philosophical assumptions. They assume everything can be quantified in terms of costs, the cost of taking a particular action, the cost of not taking a particular action. And this is totally and certainly a philosophical assumption, but it's one that tends to be relatively useful when kind of trying to quantify the impacts of various actions. So within mitigation and adaptation, there are a couple of different sectors or areas that we tend to look at as where we would actually implement these kinds of actions. So mitigation, you'll see a couple of familiar friends from the sectors part of the greenhouse gas emissions diagram I showed earlier. So we might think about, for example, reducing emissions from electricity systems or from cities or from agriculture, or we might even think about removing greenhouse gas emissions from the atmosphere directly in a concept called carbon dioxide removal, negative emissions, etc. On the adaptation side, some things we may want to do are to predict what will actually happen due to climate change at, for example, a city level, in order to allow them to then adapt to that. And we may also otherwise want to reduce societal impacts by, for example, building more robust food systems or kind of adapting to the effects of mass migrations that we will likely see due to climate-induced changes in landscapes. And then finally, I talked about sort of this, again, this balance between incoming radiation and outgoing radiation causing climate change. There are some approaches, solar geoengineering, that actually try to increase the amount of solar energy that's reflected out of the Earth's atmosphere from the get-go, in order to make that incoming arrow of how much energy is coming into the Earth smaller, and as a result avert warming. There's a lot of uncertainty around this and such, and Kris will get into this later. But this is another method that's usually thought about within adaptation. And then finally, in addition to mitigation and adaptation, there are a lot of overarching frameworks that are used to actually implement mitigation and adaptation strategies. So things like policy and markets, things like action at the individual level, education, and financial structures. And so these are also things to bear in mind as you actually go about implementing mitigation and adaptation strategies. So with that, I'm actually going to hand it over to Lynn. Take it away.
All right, so let's dive into climate change mitigation, which refers to reducing greenhouse gas emissions. And those greenhouse gas emissions can come from, for example, the energy sector or the land use and agricultural sectors, as we just have seen. And for the energy sector, we have factorized this greenhouse gas emissions in this equation here. And so the different factors here are population, service per population, energy per service, and greenhouse gas emissions per energy. And this population term is something that's not commonly addressed in climate change mitigation strategies, so we are going to focus on the latter three terms. And this equation is very similar to the Kaya identity, which uses GDP as a proxy for services consumed. For the land use and agricultural sectors, this is not as clear cut, and the equation here, like the greenhouse gas emissions, are a function of more complex changes in land use, for example, in forests and peatlands, fertilizer use in agriculture, or livestock. And we're going to start by focusing on the energy sector. And for the energy sector, I'm going to use this example of a car, which is something that's very immediate for every one of us, and it's a large contributor to global greenhouse gas emissions. And we see on the plot on the right, which shows the total greenhouse gas emissions globally from transportation, that road transportation, here in blue, takes up a very large share of transportation. And this roughly split half and half into passenger and freight. So it's a very important topic to address. So the first term here that I want to get into is service per population. Yeah, and the service here is referred to as person kilometers. So how can I bring one person to a destination? And the mitigation strategies are one's reducing demand to drive. So for example, on an individual level, is moving closer to the workplace. And on a structural level, this means to create, for example, denser urban areas where the destinations and origins are closer together. It can also mean to have more passengers per trip and vehicle. So for example, to have taxis shared by several people, or to have high occupancy vehicle lanes. So on the level of the whole energy sector, we have, this really refers to the strategy of reducing consumption. So the mitigation approaches here are both on an individual level, behavioral changes, but also structural improvements that make such changes easier. And one example that is really prominent here is the example of aviation. Where behavioral changes can have a large impact. But also such things as, for example, setting your thermostat to a higher temperature in the summer in order to use less energy from air conditioning can be such behavioral changes for service overpopulation. And also consuming less goods where there's a lot of carbon embedded in producing and transporting those goods. And the last example I want to mention here is consuming less meat, which is actually very important for the land use sector. So I'm going to get into that later. And we have several fields and areas that are concerned with these kind of problem settings. So one important one is behavioral economics and computational social science, but also urban planning, operations research, and public policy and policy analysis. The next term here is energy per service. And this really refers to efficiency. So in the case of the car, this could mean to drive more efficient vehicles, but it can also mean to drive more efficiently, so do eco-driving. And there's another strategy is to switch from those modes that are less efficient to those modes that are more efficient. So for example, from a car to a bike. And on a system level, this graph will help us to understand better what it actually means to implement this efficiency. On the left, we have all the different energy sources in the energy system. And those sources either flow to electricity generation here in the orange box, or to end-use sectors, consuming sectors, residential, commercial, industrial, transportation, which I indicated in pink here. So for example, we have from natural gas, we can either use that to generate electricity, or we can consume it in households directly for cooking and heating. And that electricity, of course, goes back into the end-use consuming sectors. And what is indicated in light gray here is the rejected energy. This is all of the energy that has not been used productively. And the dark gray indicates the energy that's actually used to generate services. So about 2/3 is actually rejected energy, and we can decrease this share by increasing the efficiency. So the mitigation approaches here are having more efficient generation technologies in the electricity sector and more efficient end-use technologies. And fields and areas that are concerned with this are, of course, the engineering disciplines, electrical, civil, and environmental and mechanical engineering, but also economics and public policy and policy analysis for creating more incentives. And getting into the last term here, greenhouse gas emissions per energy. This really refers to, in the example of the car, to switch from those high emission fossil fuel energy sources to cleaner sources or low emission sources, which can be clean electricity used in a battery, so battery electric vehicles, or alternative fuels that are generated with cleaner sources. This can be electrofuels or other syn fuels, often also referred to as solar fuels, hydrogen, and biofuels, even though for biofuels, there's a much more complicated interaction with land use, which make them not such a great technology to promote. Let's put it that way. And on the energy system level, we really have to look at renewable electricity generation here to reduce the greenhouse gas emissions per energy. And in order to be able to use this low carbon electricity, end-use sectors have to be electrified. So instead of using the natural gas in household, for example, for cooking, using an electric stove that is powered with clean electricity. And of course, the fuel switch for the transportation sector is really important. And an example here, how incentives can drive this renewable energy in the electricity grid is the feed-in tariff, where renewable energy producers, for example, solar PV owners, can get compensated better for the costs that they're incurring. So these are special policies that are designed to exactly promote this adoption of renewable energies. And fields that are concerned with this, so again, engineering disciplines such as power systems engineering or chemical engineering, but again, also economics and policy analysis. So let's dive quickly into land use and agricultural sector. So the agricultural sector and the land use sectors have actually an important share of greenhouse gas emissions. So in the plot on the right, you see the total global greenhouse gas emissions, and the green share is attributable to the agricultural, land use, and forestry sectors. And here CO2 actually plays an important role, but also other greenhouse gases such as methane and nitrous oxide. And CO2, again, is also existing in a complex carbon cycle with the land, and there are carbon sinks and sources. And a way, I mean, to view that this is a more complex way of tackling mitigation is perhaps the example of afforestation, which was in the media recently quite a bit. And here you want to make use of the fact that trees in principle absorb and store carbon, but there are many factors that make this more complicated. So for example, areas really need to be suitable for afforestation, and ecosystems can suffer from monoculture forests that are being planted. And also this measure has a very long horizon. So imagine how long it takes until a tree is actually grown. And then once that carbon is stored in a tree, it can also be easily lost. So for example, the Amazon rainforest is degrading currently, and parts of it is already a net carbon emitter. So the mitigation strategies here for land use and agriculture and forestry is really one of the main ones is preventing deforestation. And this is dependent on beef production, soy and palm oil plantations, but also mining. Another important area is restoring peatlands and coastal wetlands and preventing the degradation. Then in agriculture, reducing the fertilizer use. And really importantly, also having less cows and other ruminant animals which directly emit methane, a potent greenhouse gas. So consumer awareness here is really critical. And the example of consuming less beef here is really where that suggestion comes from, to consume less meat. Also protecting biodiversity is an important factor here, and protecting indigenous rights. And where machine learning comes in crucially here is monitoring through remote sensing can help, for example, to detect these deforestation areas. So this is where an example where machine learning technologies are even highlighted in the IPCC. So areas here where that come in are conservation biology, agricultural science, food science, civil and environmental engineering, economics, and policy analysis. And then lastly, greenhouse gas emissions can also be tackled at an economy-wide level. So for example, states or subnational institutions can set targets. And internationally, this is done through the UNFCCC framework and the Connected Conference of the Parties. So for example, the COP25, COP26. And those agreements have been in the past Kyoto Protocol and the Paris Agreement. At the national and subnational levels, of course, you have also these targets. So for example, cities are setting targets for reducing their greenhouse gas emissions. And an economy-wide tool to reduce emissions is also carbon pricing. And this price can be imposed through a carbon tax, for example, or through markets. And in those markets, there's emissions trading under some agreed upon cap. And this is also known as cap and trade or emissions trading system.
So Priya gave an explanation of kind of the physical basis for climate change and some of the main sources of emissions. Lynn described what the different kinds of levers are for mitigation. In this section, we're going to be talking about adaptation. So why is adaptation important? The idea is that many of the impacts for climate change are already being felt, right? And it's worth considering in a little bit of detail what the longer term societal impacts will be. Because if you can understand what these impacts will be, then different kinds of steps can be taken to be prepared for them and minimize the damage that's done. So that is the focus for this section. Okay, so first let's link what the kind of direct climatic consequences of climate change are with their downstream impacts. Right? So on a direct level, climate change will cause rising temperatures, changing precipitation patterns, rising sea levels, and ocean acidification. This has a kind of variety of consequences on physical, biological, and human systems. And these systems all have different interactions with one another. So for example, on a physical level, climate, like rising temperatures will cause glaciers to melt. These melted glaciers, this will cause kind of water scarcity in a lot of populations that depend on those as sources. It also puts a lot of ecosystems that depend on the services from glaciers at risk. Kind of another important point when thinking about what these impacts will be, right? Sometimes it's tempting to think about climate change mitigation as kind of a 1.5 degrees or bust game, but really it's much more subtle than that, right? Different systems have different sensitivities to changes in climate, right? And that's what this figure is communicating. So for example, even kind of tenths of a degree temperature rise will have big effects on warm water corals, while say mangrove forests will be a little bit more kind of less affected by these changes, at least up to a certain point, right? So it's worth knowing kind of every tenth of a degree matters, and different systems will have different amounts of impact as the temperature changes. Okay, so from a very high level, how does adaptation work? The main idea is that you try to prepare, right? You try to anticipate the impacts and make changes to make the impacts less damaging. And what does that preparation look like? On the one hand, yes, you try to characterize the risks, right? And second, you try to increase robustness and resilience of your systems. So we'll give a few examples of that in the next few slides. So here's an example of what characterizing risk looks like from a study. So in this figure, the different colors are different biomes. So darker green, these are tropical forests. Kind of light pink, these are savannas. Each of these small panels, they're showing the anticipated change in biome cover according to different climate models, different climate projections. Right, so once you understand how biomes are at risk, you can plan your interventions to preserve the ecosystems that are most vulnerable. Here's another example of characterizing risk, also linking these kind of basic climate projections to their localized impacts. What it's showing are the risks for drought and extreme precipitation events in England, right? So you can understand kind of the joint probability for what could be very damaging scenarios. Okay, so that's how you characterize risk. How do you try to improve the robustness and resilience of systems? Right? For biological systems, we often think about conservation and restoration. Right? So conservation, you want to prevent loss in biodiversity. Restoration, when there is loss, how do you restore the ecosystem? So you can try to imagine there are specific species that are key for an ecosystem's function. So if you understand what those species are, then you can try to preserve them better. What this example study is showing are, they have photographs of forests before and after Hurricane Maria. And what they did is they analyzed these photographs to figure out the types of trees that were able to survive the hurricane. Right? So they were able to develop like a very careful quantitative understanding of what types of species will be most robust to climate change and which ones are most at risk. Okay, in addition to biological systems, we can think through all the kinds of human managed systems and how we can make them more robust and resilient. So both food and water distribution systems can be designed to minimize impacts, right? So you can have drought relief programs for kind of immediate consequences, and you can plan longer into the future to build things like reservoirs to prevent water scarcity. Healthcare infrastructure can be built up so that they have capacity to manage with increased mortality during heat waves or with vector-borne illnesses. And physical infrastructure can be constructed to make structures more resilient to things like flooding and heat. Okay, so far all the examples I've given have been kind of taking climate change as a given, right? Or all these impacts as a given, Another way of thinking about adaptation is you can try to prevent some of these impacts from happening at all, even though there will be increases in greenhouse gases in the atmosphere, right? One of the most common proposals for doing this is to release sulfates into the atmosphere. So this mimics the effect of a volcanic eruption. And since there have been many studies of volcanic eruptions in the past, we have an understanding of how that controls temperature, at least for a few years before the sulfates fall back to the earth. So one issue is this approach is often viewed as a last resort because it comes with a variety of non-technical challenges, right? So governance issues, these are situations arise that like if one country proposes a geoengineering system for its climate, then that can have consequences for all the neighboring countries. So that could create conflict. Or termination shock, if a whole bunch of systems were very rapidly dismantled, then you would see a quick rise in temperature, and that would cause a kind of very severe disruption. Okay, so now we've seen kind of physics of climate change, the basics, mitigation and adaptation. Now let's draw in what the connections are with machine learning. Okay, so across a variety of application areas, there are a few common leverage points, a few kind of recurring themes. So let's walk through these. So forecasting, data mining and generation, and remote sensing. All of these ideas are kind of, they are useful because machine learning has a way of taking raw data, which is not directly useful for you, into kind of a distillation that is immediately actionable, right? So remote sensing, why is it useful? It can turn things like kind of raw pixel values from satellite images into, for example, the estimated carbon stock within a forest. Forecasting is useful because it can do things like taking kind of histories of transportation demands and then estimating kind of in the future for the system that I still have control over, what is the demand going to be, right? So that's forecasting, data mining, generation, remote sensing. Approximating time-intensive simulations and accelerated experimentation, both of these kind of fall under the theme of machine learning can make basic science faster, right? Whether it's in kind of the theoretical, more simulation work, or kind of in the lab in experiments. And the final group, optimizing systems and predictive maintenance. The idea here is that even when the kind of fundamental science around a system isn't changing, by improving the efficiency of that system, it can make the kind of potential carbon mitigation impact or adaptation potential much better, right? So even if you don't change the kind of chemistry of a solar voltaic, if you can increase the efficiency of an entire solar farm, that changes the economics entirely, right? So that can increase the adoption of renewables, for example. So let's explore some examples. So accelerated experimentation. So the idea is in a lot of the basic science that is relevant for climate change, you have to work with systems and you have to actually kind of intervene in them in a sometimes very time-consuming process. So for example, if you're designing a new fuel or designing a new battery charging strategy, or even kind of tinkering with different fusion protocols, these are examples that we've seen throughout the workshop. In each of these, it usually requires some sort of tuning of kind of experimental configurations to figure out what configuration really works well and which ones are kind of dangerous, right? So machine learning, this is basically an exploration-exploitation trade-off. And machine learning can be very useful for assimilating, combining all that information from past experiments to guide you for the configurations you should try in future ones. Approximating time-intensive simulations. Okay, the idea here is that in many fields, there's a very careful understanding of the actual mechanics underlying kind of either, say, climate science, clouds, temperature, or kind of energy economics, right? Kind of demand from users over time. right? So you can build a simulation based on that basic knowledge. But these simulations are often very slow, right? So what machine learning can be very useful for is once you've learned the mapping from simulation configurations to simulation output, you can try to then, in the future, avoid running these very expensive simulations and instead just directly map from these input parameters to what the output would have been if you had actually run that experiment. Okay, and remote sensing. So kind of satellite data, very plentiful. We'll have a session after this on remote sensing. So if you find this kind of material interesting, hang around. And what's useful here is that we can take kind of raw pixels into information that's very directly useful for climate change action. Right? So this example on the top right, it's taking these images of the roofs of homes, and it's calculating how much solar panel area different cities have. So you can now start monitoring the amount of solar cover, even though there's no centralized database for that. And forecasting. So forecasting is useful both in mitigation and adaptation. In mitigation, it's very useful because if you want to optimize some system in real time, it's helpful to know what transportation demand will be like, or electricity demand will be like in near future. For adaptation, it's worth knowing for a particular area, 10 years in the future, what is kind of the average precipitation going to be? What is the typical temperature extreme going to be? So yeah, forecasting, knowing the future is helpful for both these tasks. All right, so those are some examples of some of the themes at least. Now, let's think about not just how machine learning can be useful in climate change, but how you should go about doing machine learning for climate change problems. So the first point, flashy sounding problems are not necessarily impactful, right? So kind of when people think about technology for climate change, often their mind goes straight to fusion energy. While this is an interesting thing definitely to be exploring, there are many kinds of problems which might not come to mind right away, but which are extremely impactful. So kind of example, we've been talking about methane detection, right? And this is something that only emerges when you really immerse yourself in the field. Okay, fancy model does not make a better solution. So there's this idea that just building a machine learning kind of a simple baseline, and what the machine learning community might call a simple baseline, might actually just outright solve your problem. And second, if you do want to do some sort of more advanced methodological work, then it's very important to have a sense of what that baseline would look like. Right? There is no MNIST for climate change, at least in many kinds of problems. Right? So it's very important to try kind of what might seem like the most obvious approach first. Third, rebound effects. Just because something is more efficient doesn't necessarily lead to decarbonization. Right? It's very important to think about any kind of efficiency gains within the context of their carbon impacts. And finally, don't work in isolation. Right? A lot of these projects, for them to be really successful, they need to be developed in partnership with people from across several domains. Right? And it's kind of the more this expertise is shared, the better off the chance is going to be for actual deployment and impact. Okay, so just reiterating, kind of machine learning is relevant, but collaboration is key, right? The problems that you work on should emerge from the domains that are already working on climate mitigation and adaptation. And kind of we leave with a roadmap. So learn, collaborate, listen, and deploy. It can be kind of a humbling experience to enter a field where you know very, very little. But that's where the most interesting and valuable projects is going to come from. So just recapping what we've talked about in this whole tutorial, we've explained the physical basis of climate change. We've analyzed the activities that are responsible for emissions. We've given you some conceptual tools for reasoning about the different levers for mitigation. We've talked a little bit about adaptation, and we've reviewed some overall themes and considerations for machine learning. And if you found this tutorial useful, we recommend you check out Climate Change AI. We're very actively putting together resources to help support all of you in the community who are interested in working on climate change and machine learning projects. So with that, I think we are ready to take some questions.